Headlines frame the CIA chief's comparison of AI to nuclear weapons as a geopolitical or software threat. The physical reality is an infrastructure crisis that makes building these systems harder than building a nuke plant. While code can be copied instantly, you cannot copy power plants or cooling towers fast enough. This video explains why the constraint isn't intelligence. Its physics, heat density, and grid capacity are now the true bottlenecks of modern warfare. When we hear about AI becoming as dangerous as nuclear weapons, our minds jump to algorithms making decisions faster than humans can stop them. We imagine a software glitch or a rogue code that triggers catastrophe from a keyboard. But if you look at the actual engineering required to make these systems function, the comparison holds true for entirely different reasons. You cannot simply download a weaponized AI capability and deploy it on a battlefield. The real story is one of concrete poured over decades, gigawatts of electricity siphoned from strained grids, and cooling towers that must move mountains of heat away from equipment running at temperatures rivaling nuclear reactor cores. The fundamental shift in this engineering landscape begins with the sheer density of power required to run modern artificial intelligence. In a traditional data center rack, you might expect 10 to 20 kilowatts of power consumption. That is enough to run hundreds of computers and keep them cool with standard fans blowing air across circuits. But as we moved into high-performance AI training clusters, that number jumped by an order of magnitude. Modern AI racks now generate over 100 kilowatts per unit. To put this in perspective, the heat density generated inside these servers is comparable to a nuclear reactor core, yet it is concentrated within a much smaller physical footprint than a power plant or even a traditional server farm. This creates what engineers call the heat density paradox. You're trying to dissipate massive amounts of energy from devices that are packed together so tightly that standard air cooling simply fails. Trying to cool these racks with forced air fans is like trying to cool a car engine by waving a piece of cardboard at it. The physics just do not work when you push power densities this high. The heat builds up faster than it can be moved, leading to immediate thermal throttling or catastrophic hardware failure. To manage this load, facilities must abandon air cooling entirely and re-engineer their entire infrastructure for liquid immersion or direct-to-chip systems. This is not a minor software upgrade. It is a fundamental rewrite of the facility's design because the physics of heat dissipation now supersede raw compute speed as the limiting factor in deployment. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Once you solve the thermal problem, you run into the next massive wall, the grid itself. The global electricity demand from data centers is projected to rise by 40 gigawatts by 2030, driven largely by these AI workloads. This is a staggering increase that requires building new power generation capacity at a pace we have never seen before in peacetime infrastructure projects. But it is not just about the electrons. It is also about water. Unchecked growth could require up to 1.1 billion cubic meters of water annually, which is equivalent to the household usage of between 6 and 10 million Americans. This creates a severe siting crisis where you cannot simply build these massive complexes wherever land is cheap or close to urban centers. The logic that dictated building tech hubs in places like Nevada for decades has broken down due to drought conditions. The water scarcity there means you are fighting the environment just as much as your competitors, forcing a strategic shift toward wind-rich regions like Texas and Montana, where cooling resources and power availability make more sense. This turns AI deployment into a complex engineering puzzle of geography and resource management rather than a simple software rollout. You cannot build these systems in arid zones without massive financial investment to bring water or develop alternative cooling methods, making the timeline for expansion measured in years of construction, not weeks of coding. This physical reality creates a unique vulnerability that defines the threat level compared to nuclear weapons. Nuclear arsenals are built with immense effort and take decades to expand. You cannot just wake up tomorrow with more warheads than your adversary because you have to mine the materials and build the reactors first. AI systems face the same constraint. The hardware must be fabricated, shipped, installed, cooled, and powered before a single line of code can run effectively. This means that even if an algorithm is theoretically perfect, it cannot exist without this massive physical footprint that takes years and billions of dollars to construct. The speed at which these systems operate creates what experts call flash wars. Paul Scharr, the former Army Ranger who led the Pentagon team drafting U.S. autonomous weapons policy, has noted the pressure to match adversary speeds risks removing humans from decision loops entirely. We see echoes of this in history. Back in 1983, Soviet Lieutenant Colonel Stanislav Petrov prevented a potential nuclear war by ignoring a false alarm system that would have launched retaliatory strikes based on automated sensors. The danger is not just the speed of the machine, but the fact that you cannot run an AI-driven conflict faster than your cooling infrastructure allows without triggering thermal failure. If the grid falters or the water supply dries up during a critical escalation, the weaponized system does not just stop, it becomes physically incapable of functioning. The environmental impact spans three distinct phases: mineral extraction for hardware, energy-intensive training simulations that consume vast amounts of power, and operational deployment where the heat must be constantly dissipated. This physical footprint is entirely different from older rule-based systems like the phalanx close in weapon system, which required minimal power compared to modern machine learning-driven targeting. The constraint isn't intelligence, it's physics. You cannot run a system faster than your cooling infrastructure allows without thermal throttling or fire hazards. Grid capacity constraints, rather than software bugs, currently act as the primary bottleneck for AI deployment expansion globally. The threat is not just that an algorithm might make bad decisions, but that you need a whole new power grid and cooling infrastructure to make these weapons work, making them vulnerable not to hackers but to brownouts and heat waves. The comparison to nuclear weapons holds true because both require massive, slow-to-build infrastructure that defines their strategic value and vulnerability. When the CIA chief speaks of AI as a weapon on par with nukes, he is acknowledging that we are entering an era where the limiting factor for warfare is no longer just code or strategy, but the ability to keep the lights on and the machines cool in an increasingly resource-constrained world. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.